Today, I'd like to talk about learning and neuroplasticity in leadership context, because this is a very interesting and demanding topic. Learning and neuroplasticity in leadership context. How do we become a good cellist, a good reader, writer, juggler, or leader? By learning how to do it. In this presentation, I'd like to talk about the neural foundations of learning and how we can strengthen them in our leadership context in schools, universities, or learning business organizations. Let's take a look at the agenda. First, we will define what it means when we talk about learning. Then we will talk about neuroplasticity as the basis of learning processes and the amplifiers of plastic processes. And finally, we will talk about strengthening plastic processes in leadership contexts. So first of all, learning. From an educational and psychological perspective, learning is a relatively permanent change in behavior based on experience and cannot be attributed to innate or genetic dispositions, as Bauer and Hilgert say. Behavioral change is thus considered to be the most important indication of learning, and it can be a motor, physical, cognitive, or emotional change. Accordingly, one becomes a good cellist, reader, or leader by learning a new behavior. But how does one learn a new behavior? By changing the functions and structures of one's brain, thereby adapting them to an experience. For example, to the challenges of being a leader. Changing the brain based on experience is called neuroplasticity. Throughout life, the brain changes because it's constantly adapting to new challenges. It is constantly rebuilding itself based on the experience it has had. Plasticity is highest in early childhood, but persists into old age. The genetic disposition forms the starting point, but how strongly and extensively the genes are activated depends on other factors, for despite the genetic framework, the brain is considerably plastic through the experience a person has. Moreover, in addition to genes and experience, the environment also plays an important role. For example, many studies have shown that low stimulus and stressful environments, for example, in poverty-stricken families, lead to a failure to develop children's existing potential, as Reis and Kishiyama told us. Plasticity is divided into two types, in functional and structural plasticity, that changes the brain in different ways. Functional plasticity. So, functional plasticity is the alteration of the presynaptic or and postsynaptic activation centers in neurons by remodeling the building receptors. The functional neuroanatomical structures are thus altered. Thus, the synaptic transmission are altered in terms of their strength, stronger or weaker, and their speed, faster or slower. So this is the change of neurophysiological activation potentials as a result of experience. It changes the efficiency of synaptic transmissions in particular. The structural plasticity refers to the structural change in brain as a result of experience, that is, anatomical changes in neural networks. These are changes in dendrite trees, axons, or myelinizations. The density or and volume of gray and white matter change as a result. The thickness of the cortex in some places, or even the shape of the individual gyri. Thus, people with expertise in one area, such as musicians or chess players, have greater density, gray matter volume, and or cortical thickness at trained sides of their surrounding area. On the other hand, after amputation, there is often a reduction of gray matter in this cortical section. Eventually, functional change precedes structural change. Amplifier of plastic processes. Weak activation of synapses does not change the brain. Short-term plasticity occurs with short learning impulses, which one increases the transmission strength for a short time, up to a few minutes. In long-term plasticity, on the other hand, transmission changes for several minutes, hours, days, or for life. These occurs in particular with the regular repetition, physical or cognitive training, or as well as with the strong impulses. Both alter the brain in long term. For example, showed seniors a massive increase of gray matter in the area of MT for visual perception, campus, as well as in the hippocampus after 3 months of juggling training. This provided a clear evidence of structural plasticity in the elderly brain. For example, Malikan students showed an increase in gray matter before testing after 3 months of learning, as an investigation of Draginsky found out. For example, after a 6 months balance training, 45 minutes per week, gray substance increased in the prefrontal cortex, as Taubert found out. Nordic walking training, the hippocampal volume increased and memory performance improved, as Erickson found out. Swiss neuropsychologist Lutz Jenken concludes that even a short training session leads to measurable anatomical changes. The more intensive and in-depth the training, the stronger the changes in the brain. Repetition is thus central for plasticity, as Buzz and his college noted. Thanks to plasticity, the brain adapts to what it does most. In this context, it is also exciting that people who had only practiced mentionally also showed increase in the area of the activated volume. Physical damage after accidents can also be compensated by the brain through repeated training. Brain stimulations by deepened training or by deep brain stimulations by an insert electrode, which calms or stimulates an area of the brain by electronical impulses, show strong effects. Here, for example, the electrode is attached to the parietal lobe and accordingly sends electronic stimuli to a sensitive motor system. These neurotechnological interventions connect the brain at a human-machine interface by the surgical implant. The implant connects human and computers and then stimulates the brain area on the cortex responsible for this specific behavior. It's a brain-machine interface. And what reinforces the plastic processes beside training through repetition and technical brain stimulation? The so-called brain-derived neurotrophic factor is an important hormone and fundamental to neuroplasticity. Training, repetition, challenges, exercise, rest, sleep, and good nutrition all contribute to BDNF production, as Hansen and Russell. So brain-wise leadership. On the leadership side, research has shown that good leaders especially provide safety and cognitive stimulation to employees that avoids continuous stress. It is also essential that healthy, supportive relationships are fostered and competitive or exclusive behavior is minimized. This is because prolonged neural stress adversely affects cognitive functions, increasing the amygdala's fear response, inhibited hippocampal activity, and thereby reducing neuroplasticity or even promoting neurorigidity, which is the opposite of neuroplasticity, leading to less adaptive behavior. Brain-wise leaders also exhibit a growth mindset in the sense of Carol Dweck. Finally, they allow people to have the very experience that plasticity supports, namely time for training and repetition, challenges, opportunities for movement, periods of retreat and rest, and a good provided nutrition. Leaders who promote such measures in schools, universities, or companies are on the way to brainwaves activating the full genetic potential of their pupils, students, or employees. High neuroplasticity and thus deep learning become possible. Thank you for your attention. Bye.